So most of the work will just adopt a straightforward sheared slab geometry, and this will be what I call the reference state. So I'll be thinking of this as my basic state, and to this I'm going to add a magnetic perturbation, and I'll think of the magnetic island as a perturbation to this reference state. So it's the standard slab, standard for the tokamak anyway, with x in the what we call the radial direction. So flux surfaces are surfaces of constant x for us. The field is predominantly in the z direction, but there is a sort of a twisting field increasing in the y direction. So we can represent it as a dominant field in the z direction, and then a flux which only varies with x to give us this y component of the magnetic field. So that's going to be my basic reference state, and the distribution function I'll adopt, the reference distribution function, will just be a Maxwellian constant on the constant surfaces, surfaces of constant x.
So will you assume that field lines bite their tails in the z direction at x equals 0?
At the rational surface, yeah, where the island is, yeah. Oops. So we add, as I say, a magnetic perturbation. So I add this piece here, which gives me the magnetic island. So it gives me this island structure here at the position where x equals 0. And the amplitude of this, psi tilde, is just related to the island width. So psi tilde is proportional to the square of the island width. So that's one thing that I want you to try and remember, is the link between the amplitude of this magnetic perturbation and w is that w squared is proportional to psi tilde. Another parameter that's convenient to introduce is this psi variable. And I only introduce this psi because I'm periodic along the y direction, so it's convenient to introduce psi such that psi goes from 0 to 2 pi in the y direction. But just remember that psi is really a y variable. Go from 0 to 2 pi as I go from one island x point to the other island x point. So what I'm going to do in this talk is I'm going to calculate what the response is, the gyrokinetic responses of the electrons and the ions are to this magnetic perturbation, adding to the basic reference Maxwellian, and a self-consistent electrostatic potential that I don't know yet, but I'm going to determine that by quasi-neutrality at the appropriate time. You can then calculate a current perturbation from these responses, and we'll feed that back into Ampere's law to get a self-consistent relationship for the amplitude of psi tilde, or the island width, either. Yeah? No. The guide field is much, much bigger. As Bill was saying yesterday, in a tokamak it would be like a factor of 100 to 1,000 times the size. This is compared to x, yes. So x over ls will be a small number. Yeah. So the first thing I want to remind you of is the concept of delta prime. So we want to solve for the psi tilde, and over most of the plasma, except near the rational surface, we can use ideal MHD to solve for psi tilde. And if you apply boundary conditions, so in a tokamak you'd apply a boundary condition at the center of the plasma and at infinity or at a wall here, and you'd solve the ideal MHD equations, you'd get some solution for psi, which you can match the amplitude of psi at the rational surface, but you won't generally match the derivatives of psi at the rational surfaces here. And this derivative of psi, this jump in the derivative of psi across the rational surface, this layer around the rational surface, is parameterized by a thing we call delta prime. So delta prime is just 1 over psi times the difference in the derivatives of the radial derivative of the psi across the layer. And so this delta prime parameter has got nothing to do with the layer, and most of my talk today is going to be about the layer. This is probably the last time I mentioned delta prime, so it's got nothing to do with the layer, but rather characterizes the global properties of the equilibrium we're looking at. So in a tokamak it would characterize the free energy and the current density gradient, for example. Now let's go into the layer, and let me look at a sort of a simple layer where psi, I'm going to be using the so-called constant psi approximation for everything that I say. I've got enough problems without going away from that. So psi is going to be roughly constant within the layer. So now we're just looking at a very small radial region around the rational surface. Psi looks roughly constant, but in this situation it's changing sign as I go across the rational surface. And so there's this jump, as I said, in d psi dx as you go across the rational surface. And that jump in d psi dx gives you a spike in the second derivative, d2 psi dx squared at the rational surface. Now d2 psi dx squared is just related to the curl of the magnetic field perturbation that I've introduced for the island. In fact, it's the parallel component of it. So this d2 psi dx squared is just the parallel current through Ampere's law. So maintaining this d2 psi dx squared in here, you need a very localized current density in the vicinity of the rational surface. So I can integrate this now out to large distances using the fact that J parallel is localized, and integrating this, I just get the jump in d psi dx across the rational surface, and that's got to match to the ideal MHD solution, so that brings me delta prime into the equation. And this, I'm just integrating across the layer, so I just get a J parallel here. And this is the basic tearing mode equation, and the different models for the basic tearing mode equation are just different models for this current density that appear in the layer here. So just to expand on that, we've got the left-hand side here represented by delta prime. This characterizes the global properties of the equilibrium, the free gradients, the free energy in the gradients, such as the current density gradient, to drive these tearing modes, drive the magnetic islands. That's represented by the left-hand side. And then the right-hand side is the localized physics around the rational surface, localized current densities. And it's this which generally creates all the problems, although there are difficulties in determining even delta prime in a toroidal plasma, for example. But I'm going to focus mainly on this, as I say here. The different classes of tearing mode that we talk about generally are related to different pieces of physics driving these parallel current perturbations. The simplest and most established nonlinear tearing mode theory was that introduced by Rutherford, where he said, let's take the current density perturbation that's just driven by the inductive electric field. So as the island grows, you get an induced electric field because you're changing the flux up through the island. Okay, so you get just a resistivity A to J parallel is E parallel. And there's two pieces with the E parallel. One is the inductive electric field, and one's due to an electrostatic potential, which might be set up, and we'll come to that shortly, because of the different responses of the electrons and ions to the island, for example. Now, in the absence of any perpendicular drifts, so let's forget drifts for a moment, I'll bring them in shortly. If there's no perpendicular drifts, all of the current this current will be in the parallel direction, and therefore the divergence of J, which has got to be 0 from quasi-neutrality, is just going to be grad parallel J parallel. And so this quasi-neutrality basically tells me that J parallel has got to be constant on flux surfaces. And this means that I can average this equation around a flux surface. So I define an averaging operator which just annihilates the grad parallel operator. And that gets rid of phi for me, and I get a straightforward relationship between J and some geometric factor and d psi dt. Remember, psi was proportional to W squared. W is the island width, so this looks like W times dW dt. So I can just stick this now back into my basic tearing mode equation. Remembering this looks like W squared, so I've got delta prime times W squared. This now is a W dW dt, and I get another W from integrating across the layer. So I'll have W squared dW dt here, W squared there, and basically get a dW dt balancing delta prime. And that's the standard Rutherford result, that that an island will grow on a resistive diffusion time at a rate proportional to delta prime, linearly with time. Okay, so that you all know. So now how do we bring in the drift model? So I'm just going to extend this now. I'm going to pull out that inductive field, and I'm going to write my basic tearing mode equation now as a W dt, this delta prime piece, and any other currents that I wish to introduce. And in particular, I want to bring in what would happen to the E cross B drift and how this would get into here. Well, if we consider small magnetic islands, then the responses of the electrons and the ions to the small magnetic islands will be different. Okay, and so there will be an electrostatic potential set up associated with the island, even though it's only a magnetic potential that we've imposed. Now, if that island width is small, comparable to the ion Larmor radius, say, then the ions will see a gyro average of the potential, which will be different to the local potential that the electrons will see because of their much smaller Larmor radius. So the two species, the ions and the electrons, will see different effective electric fields. One's a gyro average, one's the local one. And because they see different effective electric fields, they see a different effective E cross B drift, and therefore this drives a perpendicular current, which is another way of looking at the ion polarization current, it turns out. So this, of course, is a perpendicular current, a current across the magnetic field lines, whereas what I need to put into here is a parallel current density. That's what drives the island. However, this current here is not divergence free. It has a divergence, but the total current must be divergence free, and so this drift drives a parallel return current through the electrons, such that the divergence of the total current is 0. And it's this parallel current in the electrons which goes into here and influences the island evolution. So clearly, this is only going to be important for islands that have a width of a few iron Larmor radii. If that's not the case, then the orbit averaged, then the FLR averaged potential would be the same as the local potential. You wouldn't get this difference in the effective E cross B drifts, and there'd be nothing to drive this return current in the electrons. So this mechanism is only relevant for island widths that are comparable to the iron Larmor radius. Yeah.
Is the mean free path really short enough to make the resistivity the dominant effect?
Oh, no, maybe not. No, I agree. Yeah, that's just a model put in there for now, but it's not going to affect anything that I'm going to talk about. What I'm going to talk about for the rest of the talk is really this term here, and there may be something else that's more physical in a less resistive plasma that one would put into here to determine the time evolution. Yeah. So, but nevertheless, the mechanism is still only important for small magnetic islands. So why are we interested in such small magnetic islands? Well, first of all, one of the major interests is that if we have high mode number islands, then these will all sit on rational surfaces. Those rational surfaces will be close together. They can be comparable to the line Larmor radius, and so you can imagine situations where you get lots of small magnetic islands on adjacent rational surfaces overlapping, creating a stochastic magnetic field and driving electron transport. However, as I've already said, there is an electrostatic potential also associated with these islands, so there is at least the possibility that it's not just the stochastic magnetic field which will drive the potential, but also drive the transport, but also the electric fields, the local electric fields around the island, which I'll describe later, can drive an electrostatic transport process, and therefore it's not inconceivable that these can also influence the particle and the thermal transports. But that hasn't been worked out, but in principle it could contribute to the particle and ion transport as well as the electron transport. Another reason that we're interested particularly in a toroidal tokamak is something called a near-classical tearing mode. And we can think of a near-classical tearing mode in terms of the same sort of picture that I've drawn up. It's a different J parallel that goes into that model, basically. So in a tokamak, there is something called a bootstrap current, and the only thing you need to know about the bootstrap current is that it exists whenever there's a pressure gradient in the plasma. Okay, so you have a bootstrap current which is proportional to a pressure gradient. Now, if I have a magnetic island, the pressure will tend to be flattened across the O point of that island, and so the bootstrap current will be removed from the centre of the island, and it's that hole in the bootstrap current which provides the current perturbation that goes into that Rutherford equation that I showed. And so you get another term here, so these are the two terms I had already. You get a term from the bootstrap current which looks like the pressure, because the pressure gradient, actually pressure gradient here, LP is the pressure gradient length scale, LQ is the safety factor gradient length scale. So you get something which is proportional to pressure and inversely proportional to the island width. So this means that this term will always beat the delta prime. So even if you're stable, according to Rutherford theory, i.e. delta prime is negative, this is generally positive in a tokamak, and for sufficiently small island widths, it will beat the delta prime. And so this would say that you will get island widths on islands on every rational surface such that these two terms balance, and so you end up with island widths scaling like the pressure. And this island width scaling like the pressure would be an absolute catastrophe for tokamaks, because it's not something you can burn through. You can't just push through this by increasing the heating power. So if you started to get these magnetic islands, you say, okay, it's degrading my confinement a little bit, I'll just add some more heating power and burn through it. But as you try and push up the pressure, all that happens is the islands get bigger and it just throws more power out. And so it basically gives you a soft limit on the pressure beyond which you can't go. And this is a major concern for ITER, for example. These were first observed on TFTR back in the mid-90s. So this is the classic paper by Chang, where they showed, so the black wiggly line here is the experimental measurement for the island width. The red trace is basically this expression, near enough. And you find that it agrees pretty well with the experimental measurement. What's changing here is the pressure, basically. So this island width is changing because beta theta is changing. And basically the theory will track it fairly well. Except notice that the island only appears above a threshold of about 1.5 centimetres. And so there is something down here which is suppressing these near-classical tearing modes, some sort of threshold effect.
And this bottom limit here is well above the resolution of the diagram?
Yes, it's way down here. Yeah. very definitely. And there have been more careful experiments done later, and they come up with the same answer, that there is a threshold of around about a centimetre. And a centimetre in a tokamak is the same sort of size as the iron orbit size, which for a tokamak is the trapped iron orbits, are the ones that you're interested in, not the Lama radius for this physics anyway. And so to understand this threshold, the drift effects are going to be important. We have to understand the physics of islands, not just at these big scales where we're worried about them, but if we want to understand the onset conditions, we've got to understand the physics of these small islands where the drift effects are going to be important. The final example that I'll give is one that's particularly topical at the moment, and that's suppressing eruptions in tokamak plasmas called ELMs, edge-localized modes. So these are basically big filaments of plasma that erupt from the tokamak plasma surface. And if they can't be controlled on ITER, then they will just do far too much damage to the first wall components and the exhaust components. So we have to try and think of mechanisms to control them. And one of the most likely mechanisms, one of the most promising ones, was demonstrated on D3D, where they just put a load of coils around the edge of the plasma. And what they're trying to do here is they're trying to make what's happened, the reason you get these eruptions is the pressure gradient at the edge has just got too big. The confinement is too good at the edge, basically, and that pressure gradient is driving these big eruptions. So we just want to relax that pressure gradient down a little bit, and the idea that the D3D guys had was to use a system of coils to actually drive little magnetic islands in this steep gradient region, and those little magnetic islands would cause a stochastic field, they thought, flush out the temperature, reduce the pressure gradient and switch these eruptions off. And it works. So this is a case from D3D. Each of these spikes is time along the bottom. Each of these spikes of light, D alpha light, shows one of these eruptions. They apply the current to these coils at this time and these eruptions go away. And if you look at the pressure gradient, while you see the eruptions, it's a big pressure gradient. This is just looking at the edge of the plasma, big pressure gradient. Later on, it's a much lower pressure gradient here. And again, the kind of island sizes, so this is not real units, unfortunately, but this is just a few centimetres across here, and we want to generate many islands across here. So the kind of islands that we're talking about to be generated here, although they're driven islands, now externally driven, are again of the same sort of size as the iron orbits, and therefore these drift effects will be important in understanding how the plasma responds to this applied magnetic perturbation. Will it try and heal the magnetic islands that you're trying to drive, or will it cause them to amplify and grow? And that, of course, is going to be crucial for getting the stochastic magnetic field here. There are other things that we don't understand here, in that it's not the temperature that's flushed out, which was initially thought, it's actually the density that's flushed out, and that's an ongoing research program, is to try and understand what's this transport process that's going on, if indeed the magnetic field there is stochastic. So that's given you some motivation, so now let me spend the next half an hour or so just looking at how do we actually calculate the plasma response and calculate the drives from this drift kinetic, for these drift kinetic tearing modes. So, as I said, the basic idea is that we're just going to impose a magnetic perturbation. This is the parallel component of the vector potential. So it's the same thing as I introduced before. We're going to expand about a reference state, which is a sheared slab, with a Maxwellian constant on the constant flux surfaces. The surfaces are constant x. We're going to, in general, an island will propagate through the plasma. Okay? And one can work in any frame that one likes. It turns out to be slightly easier if you run along with the island, so the island looks like it's stationary, in which case the plasma will have an E cross B flow around the island in general. And so my full potential has got a reference state potential, which is this. So this is the electric field associated with the fact that I'm running along in the y direction, so the islands look like they're stationary. So there's a reference state potential here, plus a localized potential, localized around the island due to the differing responses from the electrons and ions to that magnetic perturbation. And this I have to calculate. So I'm going to use gyrokinetics, standard gyrokinetics, nonlinear Friedmann-Chen equation here, where I've got the parallel streaming. This is just the non-adiabatic part of the response for ions or electrons at the moment. I've got parallel streaming here. This is along surfaces of constant psi. Surfaces of constant psi are the surfaces of the magnetic island. Okay, so this is the nonlinear parallel derivative around the perturbed surfaces of the magnetic island. This here is the E cross B drift associated with that reference electric field, so a VE dot grad. Remember, psi is really y, the y direction. And then I have a nonlinear term, gyro averaged, angle brackets with an alpha mean I'm gyro averaging this. It's highly localized on the iron Larmor radius scale, so I need to gyro average that. I could have collisions, and then I have a drive term from this reference state Maxwellian here. So omega E here, remember, is characterizing this equilibrium electric field, the reference state electric field. Another way of thinking about it is if you want to go to the frame where this electric field is 0, omega E is the frequency that the island will propagate through the plasma at that, in that frame where the electric field is 0. So we're expecting it to be something like a diamagnetic frequency. Okay, I think I said everything else. So let's have a look at the electrons and the ions in turn. And what we take initially is going to be the standard drift wave ordering. So this is just the same equation as just written down, gyrokinetic equation with E's instead of J's. And so for the electrons, the standard drift wave ordering is to say everything's dominated by the parallel dynamics. So I can immediately get rid of all these drifts for the electrons. And for the electrons, I'm basically got just balancing this parallel streaming against the magnetic perturbation. And that, it turns out, you can integrate up and integrate over velocity space. And you get, if I put the adiabatic piece back in, so you've got an adiabatic piece here, then I have this piece that looks like X is just that A parallel driven by that. So that's just integrating that up. And because I'm doing an integral at constant psi, I get a free function that I don't know, that I'm just going to call h of psi for the moment. Okay? So that's just a free function of integration from integrating this equation up. To see what the physics of this h of psi is, let me write this in a more familiar form. So remember this omega E has got this reference state electric field in. So this term here is really just a part of this Boltzmann piece. So if I rewrite this little phi as plus this omega E, I can write that as a big phi, the total potential. So it's got the reference state electric field and this, what I'll call the perturbed electric field. This omega star over omega star times x is really just subtracting off the fact that this looks like n naught of x. So I've got a density gradient here, so I've got n naught of x, and then I've got a dndr times x. So that term with the omega star E is just taking that gradient off. So what I end up with then is a Boltzmann piece acting on the density at the rational surface, and then everything else is h of psi. So h of psi is really just representing the density profile around the island. And the reason I don't know anything about it is I haven't put any transport physics into this model. If I don't put any transport physics in it, I can't know what the profiles are. Okay, so that's why that's undetermined at this level. We'll come back to determine it in a moment. Let's look at the ions now. So the ion response in standard drift wave ordering is to say that the parallel streaming is less than the drifts. And so the ion response is dominated by the drifts, and so we get rid of the parallel streaming terms and the collisions. Now this is quite an interesting equation actually, because it turns out, although this is non-linear here, it turns out that the linear solution is a solution of that non-linear equation. So you can write down this solution exactly. So if you just forget this for the moment, you can see that if I just integrate those up, I'll get that GI is just going to be phi, and then clearly this non-linear term for GI being phi would be identically 0. So you get the linear term, but I can have some arbitrary function of the total potential. So that's the equilibrium, the reference state electric field, or reference state potential, plus this perturbed potential here, an arbitrary amount of that, basically because I've got B cross grad phi dot grad K of phi. Okay? So there's another arbitrary function that comes into there, and this is just kind of associated with the flow. And we can see why it's associated with the flow. If we impose quasi-neutrality, so we take this for the ions, add the adiabatic piece, integrate over velocity space to get the ion density response, equate it to the electron density response for the previous slide, and just for the moment I'm going to expand the Bessel functions associated with the Larmor radius, with the finite Larmor radius effects. So this represents my finite Larmor radius effects now. I have a piece here which contains ITG physics through the A to I mode, and it contains the electron drift wave through this omega E minus omega star here. But there are drives. So there's a drive here, which is the piece where the electrons are responding to the magnetic perturbation, and there's another drive associated with this K of phi thing here. So to solve this, if I knew h of psi, which as I said is linked to density transport processes, if I knew h of psi, I'd still need to know K of phi to calculate what phi is. Okay, so this sort of tells me that that K, I can have a completely arbitrary flow profile depending on what K is. So the arbitrariness of K is representing the arbitrariness of the E cross B flow profile, and again, we don't expect to be able to calculate the flow profile because I haven't put any kind of dissipation in here, any sort of viscosity or anything. So the H of psi represents an arbitrariness of the density, the K of phi represents an arbitrariness of the flow profile. And this is kind of similar to the situation we have with the Grad-Strofanov equation in tokamaks, where we're solving for the poloidal flux. There we have a second-order differential equation for the poloidal flux psi in terms of two unknown quantities, the pressure profile and the current profile. In order to know the pressure profile and the current profile, we need to go to transport physics and calculate those two profiles, then we can solve for the equilibrium. This is very similar. I need to go to the transport physics to determine H of psi and K of phi, and then I can solve the equilibrium problem, in this case for phi rather than psi. Okay, so it shouldn't worry us too much. What we often do with Grad-Strofanov equation is we'll specify models for the pressure and the current profile which satisfy all the boundary conditions. Sometimes we'll go away and solve the transport problems, but usually we'll just specify models for them or take them from data. So again, we can do two things here. We can either specify models for H and K, which satisfy the boundary conditions, or we can specify transport models and determine H and K. And the former, of course, is much easier, largely because we don't know the transport physics that's determining them. In fact, K equals 0 is a valid solution. It satisfies all the boundary conditions. So in fact, a valid solution to that nonlinear equation satisfying all the boundary conditions for the ions is just the linear response. And I will take K equals 0, and virtually everybody in the past has always taken K equals 0 as well. Let's have a look at H of psi, though. You can do a little bit better with H of psi and perturbatively introduce a sort of heuristic diffusion model into our electron equation. So remember, the electron equation before was just the free streaming terms. Let me now add a little bit of diffusion into there. These two terms average over a flux surface to 0, and so this term here must also average over a flux surface to 0. And this is an equation that you can solve, and you can get H of psi. Omega here is just a normalized psi. So you can get H, which is a flux surface quantity, of course, in terms of basically elliptic integrals. You don't need to know exactly what form this is, but there's two things you do need to know that I'm going to come back to later. First of all, that this theta function here means that H of psi is 0 inside the island. Omega equals 1 is the island separatrix. Omega less than 1 is inside the island. So this just tells me that H is 0 inside the island, i.e. the density is flat. The other point to note is if I calculate dH d psi, it's going to be 0 inside the island, but it's going to be finite straight outside the island. And so there's a discontinuity in dH d psi at the island separatrix. I'm going to show you a picture of basically what it looks like. So this is the typical density profile that you get, and it's like the H of psi profile. So it's flat inside the island here, and it's got this discontinuous derivative on each side of the island. So in principle, we can now go and solve for the potential. The next stage is to calculate the current density from that response and the potential. And if you remember, what we're going to do is we're going to calculate this from a div j equals 0. What we've calculated is a perpendicular current, because it comes out of the cross-field drifts. That perpendicular current is not divergence-free, so it drives a return current in the electrons. And we can solve that by solving the divergence of the total j as 0. To get this equation, we go back to our electron and ion gyrokinetic equations. There's quite a neat trick which saves you an order of expansion. And you just take your ion gyrokinetic equations, you integrate them over velocity space, and you add them together, imposing equation neutrality. And the two k parallel, v parallel terms from the ions and electrons give you a grad parallel, j parallel terms. Lots of stuff cancels out, and the stuff on the left, which is basically div perp, j perp, is the drift effects. I've introduced something, you'll see this dH d psi appearing here. It's H is the same H that I was been talking about earlier that characterizes the density profile. I've also introduced something called phi I, and phi I is the difference between the FLR average potential and the local potential. So if FLR effects are not important, that is equal to that. Phi I goes to 0, and there's nothing to drive the parallel current, and we don't get any FLR effects. Okay, so it turns out you can integrate this exactly, and what you get in terms of the diamagnetic frequency and this omega e is just a j parallel that's proportional to phi I. This is just a flux surface average because the flux surface average of j has to be 0. That's the boundary condition on integrating this.
So this works outside of the island, but what do you do? Within the island, you plug surface
It
area?
works nearly everywhere, but I'm going to come to that in a moment. Nearly everywhere, but not quite everywhere, and it's the not quite everywhere which is the major headache. So let's just summarise where we've got to. We derived basically our quasi-neutrality condition, which is our equation for phi, if we knew h of psi and k of phi, or assumed forms of them. So we can calculate phi from that in principle. We derived J parallel in terms of phi and its FLR average, its gyro average. And we've got Ampere's law basically here. So we can calculate phi, stick it into there, calculate J, stick J into there, and find out whether this term is positive or negative, and therefore driving island growth or trying to heal the islands. Now I'm going to indicate, now I'm trying to get into the problem now. So remember, what I did in writing down this quasi-neutrality condition was I expanded these FLR operators. So this rho s squared d2 dx squared basically assumes that my Lama radius is small compared to my island width. So rho s d by dx has got to be a small number. So to leading order, let's put the k of phi equals 0. To leading order, these two balance, and I just get phi looks like x minus h. Okay, just by solving this and neglecting that for the moment. The J parallel is phi minus its gyro average, so this also looks like rho s squared d2 dx squared. So J parallel looks like phi I, which looks like rho s squared d2 dx squared. And if I do d2 dx squared on this, I'm going to generate terms that are going to look like d2h by d psi squared. But do remember that dh d psi was discontinuous at the separatrix. So d2h d psi squared has got a delta function contribution at the separatrix. So this generates two forms of current. One which looks kind of like rho s squared over w squared, outside the layer, outside the separatrix. And another one which is basically a delta function current sheet at the separatrix from the fact that h is discontinuous at this level of the theory. So that's just illustrated here. So if we look back at our island again, there's a rho s over w squared contribution from everywhere out here. Actually, there's zero contribution to j inside the island. And there's a delta function current sheet at the separatrix. So in actual fact, there's two pieces that I should write in down here for the drift effects. One from what I call J parallel outer, the current from out here, the rho s of w piece, and one from the layer current. And you might say, well, here you're integrating over a very small region, but it's a delta function you're integrating over. And it turns out within this model, these two pieces have exactly the same dependence on all the parameters. They only differ in numbers. But this one is negative, and this one is positive. This one, the layer one, it turns out is 4 times bigger than this one. So if you neglect this and just treat this outer region, as we initially did before Francois Weilbrook pointed it out, if you only keep this piece, then you get a certain sign, say for argument's sake that it's damping the island, heals the island. But if you put in this one, it would reverse the sign. All the parametric dependence stay exactly the same, but it reverses the sign. What was damping becomes growing. So this causes a real headache because now we have to get things absolutely right. We've got to calculate this not roughly right, we've got to get the numbers right because this is, say, +4, this one's -1. I want to know, is this +4 or is it something smaller than that? It's a skin current, it's a layer thing, so almost certainly what I've done so far is wrong, and I'm going to come to why it's wrong in the next few transparencies and maybe how to fix it. But we've got to get this absolutely right, the numbers right now, in order to know whether the net effect of these two terms is stabilizing or destabilizing. So the first thing you point out is that I assumed that the FLR effects could be treated perturbatively, so rho s d by dx is small. But then I said I've got a delta function there, so clearly rho s d by dx is not small in that layer, and I have to treat full Bessel function FLR effects there. And that's the first thing we did. And what you find is that reduces this thing by a factor of 2 immediately. So now this is only twice the size of that instead of 4 times the size of it. So that one thing has changed, had an order 1 effect straight away. Nevertheless, it's still bigger than it. And if you plot, so this delta pol is the sum of these two terms. So it's kind of like delta prime, but driven by the polarization current, if you see what I mean. So if delta pol is positive, the island's being enhanced. If it's negative, it's being suppressed by the FLR effects. And you'll see it depends on omega E. So this is the electric field, or equivalently the propagation frequency of the island through the plasma. So we need to know that in order to know the sign, irrespective of the sum of those two terms, and I'll come to that in a moment as well. So up here, we see that if the island's propagating in the ion direction, strongly in the ion direction, the islands are enhanced, or strongly in the electron directions, the islands are enhanced. But there are regions of propagation where the island would shrink away. you can see this region here where there's a lot of wiggles going on and something doesn't look quite right. I don't know if it's right or wrong at the moment. It's quite a complicated region, and the reason this is complicated is because in this region here, it turns out that the island, because of the short wavelengths associated with that layer again, can resonate with an electron drift wave. And this is a further headache, and what makes it interesting in some ways. So to see why you get that electron drift wave resonance, let's remember where our equation came from. So again, I've gone back to full FLR, because now I know I can't do the rho s d by dx expansion of it. So we've got full FLR. So if you remember what this was basically an adiabatic response from the electrons and a full linearized response from the ions. So this equals 0 is exactly what you'd write down for standard electrostatic linear instabilities, ITG and electron drift wave, from this side, but it would normally be equal to 0. But now it's equal to a drive because of the electrons responding to the magnetic perturbations. So we know that this has electron drift waves associated with it, which are excited at certain Ks in a certain K radials in a certain omega range. Normally, if you're away from the layer region, this will have typical radial wavelengths, which will be like the island width. So you can imagine situations where your island width is not resonant with any particular drift wave here, so everything's okay. But in the layer, there are a whole spectrum of K radials associated with the rapidly changing H of psi through the layer region. And there is always a radial wave number associated with this, which will resonate with the electron drift wave in this range of frequencies between 0 and omega star e. So what does that mean? Well, remember that for the ions, we ordered the frequency omega e to be much bigger than the streaming. And so ion-Landau resonance effects can be ruled out because generally you have your island here, your potential will be localized on a few island widths away from the island, and the ion-Landau resonance will be way over here somewhere, and we're just not interested in it. But now, if you couple to an electron drift wave, then this phi is no longer localized, but is instead an outgoing wave, transferring energy from here to the ion-Landau resonance, where it would eventually be damped. And so all of a sudden this is no longer a local problem anymore, but it does extend out to the ion-Landau resonance. And that's okay because we can reduce it to a local problem because we know that the boundary condition now is just an outgoing wave boundary condition instead of a zero boundary condition, but it's yet to be done. It could be done, I guess. It also introduces complex physics because now this is not a bound problem, but instead it's transferring energy out of the box to be damped at the ion-Landau resonance. And this therefore will allow the island to tap this ion-Landau resonance, even though this is true, and this will influence any sort of model that we have for determining this omega e that I'll describe in a moment. Another piece of physics associated with the layer is that, of course, discontinuities are not physical in plasma, so something has to resolve that discontinuity. And let's think back to why that discontinuity came around. So if you remember, we had an electron kinetic equation which looked like this, initially without any diffusion, and we introduced diffusion perturbatively to calculate what the H was. Now, because this has got a second derivative here, as we approach the separatrix, where G is going to vary very rapidly, in fact, there's a discontinuity in the derivative of G, so this is getting very big as we approach the separatrix. And in this layer, we can't treat this perturbatively, but instead it has to balance against the free streaming. No matter how big K parallel, V parallel is compared to D over the island width squared, there will be a place sufficiently close to the island where the radial wave numbers get to be so big that the D will compete with the K parallel. And this is basically what resolves the layer. This was looked at a fluid theory by Fitzpatrick, first of all, and then in a model a bit like this by Richard Hazeltine, Peter Cato, and Per Helander. So what they did was said, okay, so this is looking from so the island core is here, and this is going out in X away from the island. And they say, okay, so first of all, far away from the island. So everything we've been looking at so far is out here, and we've taken K parallel, V parallel for the electrons to be much bigger than the diffusion. Actually, we said the distribution, we didn't talk about collisions, but we said the distribution function was Maxwellian. So we have in mind that the collisions are actually bigger than the diffusion here, just to drive the thing towards a Maxwellian, which is what we assumed. So this is the kind of ordering that we had in everything that I've described so far. Gives you a Maxwellian G, and it gives you a density, which is a flux surface function, albeit the perturbed flux surfaces of the island. If we come towards the separatrix layer, then we've got to balance the diffusion and the free streaming. And this is what Hazeltine et al. Did. And what you find then is, first of all, the GE is no longer Maxwellian. Okay, there's no reason why it should be. The discontinuity is smoothed over a layer that's characterized by the ratio of the diffusion to the parallel streaming. But the density is not a flux surface function anymore. It varies as you go around the separatrix, for example. So the first problem is, how do we match this to this? There's two differences. This is non-Maxwellian, this is Maxwellian. This varies around the flux surface, this doesn't. And what we did with a graduate student, Martin James, was to identify a transitional region. See, what you've done here is you've gone from a region where the diffusion is bigger than the collisions to a region where the collisions are bigger than the diffusion. So you need to go through a transition region where these two match. And you can do that, and you can do all the matching. What's the result of doing all that? So this is that figure again, showing you the strength of the FLR effects, again, compared to this omega E over omega star. And you get the same sort of feature, that it's stabilizing if you're going slightly in the iron direction. I've thrown out this drift wave region because I don't know how to deal with it at the moment. So you're stabilizing in this region, destabilizing in this region. The dotted line is what you get if you don't put this diffusion physics in. If you pretend that the density is a flux surface quantity all the way up to the separatrix and just do the FLR thing. Okay, so this gives me the factor of 2 reduction from the simplest thing you do, treating it as a delta function. Now you see you get another, at least a factor of 2 again, reduction in this. So now these two layers are the layer and the external region are almost exactly balancing. If they do balance, I'm not going to be very happy because it's a long time to show that something's 0, but now they're pretty close to identical. Okay, it's still not 0, so there's still hope, but it shows that this is sort of really like angels on a pin now. Which way is this going to go? And it could go either way. And we're not at the end yet. So things that haven't been looked at all is, because the density varies around the flux surface in this layer, this means that E parallel will also likely be large there. And there's a nonlinear E parallel dFdV, the dGdV term, which we didn't include. So this E parallel is likely to be large there and is going to influence things. I don't know whether it's going to send this up or down. We've also got a large current sheet there, and is that current sheet stable, or would it collapse through some other forms of instabilities? Another big question. So, as I say, it remains crucial to try and determine the net effect between the two, and the jury's still out on it. Let me say a few things about there's two parameters that I've spoken very little about. There's omega E, which is the electric field, basically the reference electric field, or an easy way to think about it is what's the frequency of propagation of the island through the plasma in the frame where the electric field is 0. So there's that. And there's this K of phi function, which kind of determines the flow profile, really. Remember, we just put K of phi equal to 0, and we treated this as an input parameter. But a complete model has got to calculate omega E. If we don't know omega E, irrespective of whether we know the balance between those layer and the outer solutions, we won't know whether the FLR effects are stabilizing or destabilizing. So K of phi, as I said, determines the flow profile around the island. Omega E, on the other hand, is sort of like a global property of the flow. It's how the island is flowing through the plasma, and then the K of phi is how does that drag plasma along with it, if you like. And both of these have got to be determined together within a self-consistent theory, and there's very little done on this. People have looked at talks for determining the omega E, neglecting K of phi, including ourselves, but very few people, if anybody, has done the self-consistent problem of determining the two together. And I think it's not absolutely clear even what the formalism for doing it is. But in order to do it, you've clearly got to add dissipation. So it could be collisional dissipation, viscosity type things. It could be that there's an interaction between the island and the turbulence, and that non-ambipolar transport associated with the turbulence can drive, can influence the flows and the mode frequency. And then there are collisionless dissipation processes like the Landau resonance. Now, I've described the ion Landau resonance, but the electron Landau resonance is also rather interesting. I haven't said anything about that yet. So let me just have a one-pager on the electron Landau resonance and what sort of role that might play. So remember that we dropped all drift effects from the electron problem. Let me get rid of the layer for now. I'm not talking about the layer anymore. So we haven't got any diffusion in here. We're just looking outside the layer. So we just got the free streaming there. But now let me add the omega E back in again. I'm not going to add this term in. I've got no reason to throw it out yet, other than I can do the sums if I do. Okay, but there's no reason why it's any smaller than that, but let me throw it out just for illustration. Then what you get is you get this Landau resonance type term here. But I can group these together, and whereas before I had a d by d psi at constant psi, which is a derivative along the perturbed flux surfaces of the island, I now get a d by d psi at constant y, where y is this thing. So those two can be combined into a single derivative like that. So it's got omega minus k parallel v parallel, and it's got the cos psi. And this, if omega e equals 0, k parallel, remember, has got an x in it, so this just looks like x squared and cos psi, which is exactly what psi was. So if you drop omega e, y becomes psi. But if omega e is there, and then what was psi before becomes y now. So I can use exactly the same solution as I got for the electron distribution before. This is really just x, so shifted x. But instead of h of psi, I get h of y from integrating this up a constant y. And so now, just like before, the electron density was constant on the constant flux surfaces, the electron distribution function is constant on constant y surfaces. I can't talk about the electron density yet because there's v parallels in here now, a v parallel dependence in the G, which means this is not Maxwellian again anymore. But the distribution function is constant on surfaces of constant y. And what do they look like? Well, they look exactly like the surfaces of constant psi, except they're shifted. So these are the flux surface contours of the island, the black dashed ones. This is x along here, psi or y up this direction. So these are the flux surfaces. The red surfaces are the surfaces of constant y for a given value of this, of omega e over k parallel v parallel, basically. So you can see they're exactly the same shape, but they're shifted to be centered on where the Landau resonance is. So this is where the Landau resonance is. And basically what's happening here is you're flattening the distribution function across the Landau resonance. So instead of flattening the density across the island, you're flattening the distribution function across the Landau resonance, and this nullifies the electron damping, the electron Landau damping, unless you put in a level of collisions again. So if you put in a level of collisions again back into here, which I neglected here, then that would allow a density gradient in velocity space to be recovered, and you would get a residual level of Landau damping. So even if collisions are very, very rare, they may be important to allow the electrons to tap the electron Landau resonance. Let me just say 5 minutes about toroidal, spend 5 minutes on toroidal effects. So everything I've said so far, standard sheared slab, applicable to any problem where you have a strong guide field. A lot of us are interested in how we take these to a torus and look at small scale Terry modes in a torus. And the main influence of the torus is through the presence of trap particles. And this has two effects. I've already described one, the bootstrap current, which gives you this strong extra J parallel thing, which drives the islands up into really big islands, which are really bad news for tokamaks, of course. I've already talked about that briefly. I'm not going to address that. But there's also an impact on the ion polarization current. And I can illustrate very, very quickly what that impact is. If you go back to the picture that I described of the polarization current at the beginning, in terms of a difference between the orbit averaged electric field that the ions see and the local electric field that the electrons see. So the two particles see a different electric field, and the difference between them looks like the ion Larmor radius. Okay? Now with trap particles in tokamaks, they have an orbit which is much bigger than the ion Larmor radius. It actually looks like the poloidal Larmor radius. So this again is a factor of b over b theta, so that's a factor of 4 or 5 bigger than the Larmor radius. But it looks like epsilon to the half times rho theta I. So it's a much bigger orbit than the ion Larmor radius itself. And so you get a polarization current that instead of looking like rho I over W, looks like rho banana ion over W with an extra epsilon to the half. Epsilon here is the inverse aspect ratio. Epsilon to the half just represents the number of trap particles that I have. So you get a polarization current which is much bigger, or somewhat bigger, a factor of 3, 4, 5, bigger than the standard FLR polarization current. That's in what we call a collisionless limit, where the trap particles aren't colliding with the passing particles. Okay? Now, when the trap particles collide with the passing particles, if they can do it fast enough, such that they can resolve the fluctuations associated with the island, then those trap particles communicate that information, the information about the polarization current, to the passing particles and massively amplify it in the process. So the difference between the polarization current in a collisionless regime, when ui over epsilon is less than some sort of omega star, this is a diamagnetic type frequency, remember. So this is what you get in the collisionless regime. If in a collision al regime, when ui over epsilon is bigger than omega e, but not so large that the trap particles don't do their full banana orbit, so new stars still got to be less than 1. Then you get a huge enhancement, a factor of 10 or 15 enhancement of the polarization current in a tokamak. And the relevant length scale becomes the trapped ion orbit width length scale, about 1.5 to 2 centimeters, which is what the threshold was of the NTMs. This is why this sort of physics is important for understanding the neoclassical Taylor threshold. So we had analytic limits before. Andrei Smolyakov looked at the fluid limits, this collisional limits, where the polarization current is really big. So this is again this delta pole. This is the contribution of the polarization current to the magnetic island evolution. And I don't know what the sign is, so don't read this as positive because we don't know which is the biggest thing. Actually, all we've been looking at here is we've not looked at the layer contribution. We've just looked at the contribution outside the layer because the layers are too difficult for us at the moment. So this is what Andrei Smolyakov derived up here, the fluid limits. We looked at the collisionless limits shortly after, and sure enough, here you see this big difference between the collisionless limits and the collisional limits. This is as you're varying nu over omega. Eta sits here. Okay, this is a log scale. So eta is going to sit robustly in here, in this transition region where we can't do the calculation at the moment. But Koki's done a calculation and shown that he can basically connect as you would have expected in some sort of S shape through here, but with a dominant contribution coming from the layer, a very narrow layer between the trapped and passing boundary. That's why that you get this correction that looks like the square root of nu rather than a correction that looks like nu. So a correction that looks like nu would look like this dashed line. Correction like root nu looks like this line. So for eta, you can get like a factor of 2 or 3 enhancement from this collisional effect from this layer between the trap passing boundary. So you've got to resolve that layer in order to describe this region properly in a tokamak. So that brings me to the end. Let me just say a few words of summary. So I've shown you that finite ion Lama radius effects will influence the magnetic island evolution, or will probably influence the magnetic island evolution, unless there's some magic which says this layer contribution, the external contributions to the current perturbation will exactly cancel. The theory is still incomplete. We kind of know what ingredients have to go in there, but it's not easy to put them in there, both analytically and because of all the layers involved, it's going to be difficult numerically as well. FLR effects, of course, are crucial. There's cross-field diffusion competing with the parallel streaming. You have to allow that to happen, so very different length scales there in order to get the layer around the separatrix correct. Parallel electric field we haven't looked at all yet, really, in the layer, and this could be very important in the layer around the separatrix. And this coupling to electron drift waves is especially interesting, and how that allows the island to couple to the ion-Landau resonance, and possibly provide rather a neat theory for determining the flow profile and the omega E in a self-consistent model. So I say here, toroidal geometry has got additional challenges associated with it. There's not only the spatial boundary layers that are identified here, but there are velocity space boundary layers between the trapped and passing particles, which you're going to need to resolve. And also the collisional effects are important, even when you're in a collisionless regime, for enhancing the polarization current above the collisionless level. And I'll just finish with a statement that's probably now obvious from what I've said. The FLR is stabilizing. Whether it's stabilizing or destabilizing still remains unresolved. Okay. Oh, one thing I would say, actually, if it's destabilizing, tokamaks wouldn't work. So there's a lot of evidence to say that it's stabilizing. The confinement would just be terrible if this was destabilizing and you had islands everywhere. So either there's another piece of physics to add to this, or FLR effects need to be stabilizing. Okay, thank you.